Cheers. So what's Ceramic first, right? So Ceramic is verifiable event streams. It's an event streaming system. It's decentralized, and it's eventually consistent and going for scale, right? So what is the stream in this case? What's that actually mean? And what can you do with it? You can pretty much store any kind of data you want. You can build databases. We have ComposeDB. The Orbis team just released OrbisDB on Ceramic. Kind of digging into a stream here, we have basically an append-only log of linked commits. So we have the init event, which is gives a CID to this data, and it is the immutable stream ID for the life of it. And then we have data events, and these are basically signed by a user, usually a decentralized identifier, DID, but a public-private key pair that verifies that they did mutate the content of the stream. And then we have time events. Time events are rolled up into a Merkle tree, put on the blockchain, so you can verify across the entire network that something happened, in some order. So there's a time. And the key point here is that a stream can only be added to, so it's a grow-only set, and then across the entire network, the set of streams is also a grow-only set. So, what does this look like in the peer-to-peer setting? Oh, that's in the wrong order. Where's that slide? Oh no. Sorry, so it went missing. Yeah, we added it, but it's not there anymore. Anyway, so sorry, I guess we'll just use this one instead. So there's basically the node itself has like a set of streams that it's writing, and it's writing these streams. It has to verify the signature. It applies this to the local state, and then it publishes this out to the network. So all the other nodes on the network that care about the stream have an interest in this, and currently this is like an implicit concept. Like the topic, we use one topic in Gossip Sub for the entire network. So we publish these events to everyone. Most people ignore them because they don't care. The people who do store this data, verify the signatures, and then they actually take that CID and they go to IPFS and they go load these blocks using BitSwap and IPFS. So what's the problem with the way we're doing this now? Well, the main thing is most people are hearing a bunch of stuff they don't care about. So we don't want to send all these messages to everyone that they just ignore, right? And we could partition the network into more pub subtopics so that it's whether it's by the stream. So I guess backing up slightly, the stream itself is usually one of two types. The first type is a model, which is basically a schema. You can think of it as the table. And then there is the model instance document. So these would be the rows of things that conform to the schema. As you write them, they're validated, and then they're distributed to the network at that point. So we're publishing all this information that people, a lot of people don't care about, but more importantly, if you go offline and you miss all these messages, there's no good way to get them back. And if you cared about that, you have a hole in your data that you have to try to figure out. And we have a couple mechanisms currently, one of which is called historical data sync, where you go to the blockchain and crawl and load up all these CIDs and try to rebuild this train, which works, but it's kind of experimental. And then you can just query the whole network, be hey, what's the state of the stream? And then everyone will send you back the state. But that's not fast. If we're trying to go for scale here and speed, and there's no global consensus, so if you have to go ask every time you want to change something, you can't go fast enough. So we really focused on solving this durability problem, and we needed a new way to discover data across the network. And that's where Recon comes in. So Recon is a synchronization protocol. Its goal is to answer the question of what data do I have that you're interested in, and then what data do you have that I'm interested in, so we can exchange it. It's not the message delivery protocol. It's just purely an agreement of whether or not we're in sync. So how does this work, and what does this look like? Well, a key point about Recon is that it happens pairwise. Previously, we were broadcasting the entire network, but now we're having a peer-to-peer conversation. And you think that this might be slow, but it's actually going to have exponential growth because I'll tell one peer, you'll tell one peer, and then I'll tell one peer, and it's factors of 2. So it pretty quickly goes to the entire set of nodes that are actually interested. And then a key point on that is that this is the interest ring, right? This isn't the entire network. This is purely the set of nodes that actually have an interest in this data and want it. So like that set is not going across the entire network necessarily. You know, and looking at like that, like first there's the concept of how do you find your interests, which we'll get to, but first we'll talk about like how we do this. And it's inspired by a paper called Range-Based Set Reconciliation by Alosha Meyer, which basically describes a protocol to compute the union of two sets over a network. You need to use a grow-only set, ideally, or tombstones. You need a total ordering of your data, which is how you get the range aspect, which we'll get into. And you need to have an associative hash function. So you need to be able to take the elements of the set, hash them, and add them together. So the algorithm itself is actually pretty straightforward and just relies on divide and conquer. But the paper goes into like a lot of detail to like why this is mathematically sound, et cetera. So we'll just kind of skip to the interesting part. First, a quick refresher on associativity. Change the order of the hash, same hash. So with that in mind, here are the core cases of the algorithm. And the main assumption is the fact that if you hash every element in a set, add it up, compare that hash, like those two hashes match, the sets are the same. So we can do this with our set of data. We have a total order. We split that into a range. We hash all of our elements. We send that to our peer. They do the same thing. If we match, we're in sync. We don't have to do anything. There's another case where like one node doesn't have any data, which is actually pretty easy because now I just send the delta directly to them. There's no like work needs to be done other than like here's all the data you're missing. And then the main case is we have two different hashes. We have two different sets. And we basically just split our ranges, calculate a new hash, send that, and then we start recursing down the network, or just recursing down the tree, and it's basically binary search, which is a logarithmic process. So we can do this in logarithmic round trips in the worst case. So that last one is like probably worth an example. So since we have a total ordering of our ring, like you could think of this as all the streams in the ceramic network. Like we'll just use like simple string keys here, but we have two nodes that have two sets. It's ordered, and then we want to calculate the union. So you basically you start by extending your keys and your range, and they immediately discover a couple keys that they don't have. They find ape, they find GNU. They add that to their set, and then they split their set because it's a different hash, and they calculate a range. They send that back, and then at the end they added hog where they didn't have anything after GNU, so they just added 0 in hog, and it kind of goes back and forth as we split and discover. And like the two key points to take away here is like whenever there's a 0, it basically just means like send me the n keys that are missing. So you don't have to so having a contiguous range of differences is a better case than having an interleaved set of differences. And then the other case here, you can also see like on round 4, we have two ranges, but we see that they're actually like, the two ranges can be consolidated when we respond into one because we have the range of like eel, fox, GNU, and hog. We can just add that into one range and reply. So ranges can be merged as the back and forth happens. And as we discover all of the keys, we then discover that we are now in sync, and we can end the conversation. So this is about discovering like keys in a set, but so this is like we were broadcasting this to the gossip subnetwork. Like these are the keys, but we still need the data and the values. So the actual conversation is a little different than that. So the Recon is implemented as a libp2p protocol. It's generic over the data and the hash function as long as it's associative. It's currently like very specific to what we're doing, but it could potentially be useful in another way in the future. The first thing that happens is you exchange your interests. And interests are basically going back to this ring. You have all the streams in the network, and we've defined this order as like model controller, which is the user that's signing this data, the time that it happened. So you can basically declare that I'm interested in a model, like in this hierarchical order, all the data for this model, all the data for this controller and model, and like so on. And then when two nodes start this conversation, they Man, these slides are out of order. They start the conversation, and they basically say, like, what's the intersection of our interests? And we immediately say, like, I'm interested in dogs, you're interested in dogs and cats. We like just are gonna talk about the dogs key space. And we just start doing this range request, range response, and ranges are keys. In the previous example, we call them ranges in the code, but they're just keys. And then as we discover keys that we didn't have, we say, I would like the value for that key. And the key is basically a CID, so it has some metadata around it, but you can compute that the key and value match just from getting the value that you weren't lied to. So you can like, rebuild and verify that that is the right value for that key. And then we just go back and forth. When I initiated this conversation, I find all the keys and values I'm missing. I send a listen only message. You send me all the values that you discovered that you want, and then you send a listen only, and then we are done and hang up. So there's a couple of just observations here. First thing is we're doing sum of SHA-256 hashes for our sets. We wanted to avoid collisions. And we chose sum over XOR because we wanted, if we added an element twice, we wanted to make sure that we had like a bad hash that was easily identifiable in code as opposed to like a missing key. It's just a little easier for debugging. And importantly, this is not a Merkle tree. So like this is an associated half function. A tree would be a great way to store these values, right? Because we're doing binary search. So we can like in every leaf node, we can actually store the sum of the hash of the subtree. So like it's really fast to compute like what is the value I need to send you. But the storage can be different on both nodes. There's no like requirement that they match. So if we have two nodes, we can have like the first node have a fan out of 3, and the second node have a fan out of 2. And if like we're going to do Recon over the B to O key space, like the first node has like a very natural split on disk that's like super fast. Whereas the other node is like, I need to do some traversing, but like it'll still find the same values, the same sum, and it is going to be able to do the protocol correctly. So the wire format stays the same, but the implementation details have a lot of flexibility, which like lets us do some interesting optimizations. I mean, you can also just do a linear scan, add up all the data every time, and like it's fine. It's bad, but it's fine. So with that in mind, a couple of the optimizations that are possible is like, as we discover keys, like if I get to like the last, like I know this range only has 10 keys, like rather than split that range, I'll just send you all 10 keys. And also, so like the search is going to be logarithmic as we go. We have to potentially find all of these keys, but if I have a high latency network and I want to try to shorten that number of trips, I could send you, instead of just sending you one split initially, I could send you like 2,000 ranges. And you could, you might already have a bunch of them. I do more CPU requirements than I need to, but you could then, just look at those and respond to them one at a time, all 2,000 at once. For every split, that becomes 2 new messages, so like it can like grow the amount of work you have to do, but the peer is allowed to respond to one thing at a time. And this is actually really nice because it gives an asymmetry to the network, which is useful in our case because we might have a node in a server that's like massive with petabytes of data, cares about everything in the world, and we might have a node on a phone that like only cares about my user data. And we want these two nodes to be able to do Recon and just like discover any data without, and that's perfectly fine because they won't have to discuss anything that I don't care about, and it won't matter to me that I'm tiny and they're massive. I can respond with just like one message at a time if I don't have the memory or CPU to handle that. And I'm going like way faster than I intended. I don't have my notes but I think that's okay. Fundamentally, this is like a pretty big paradigm shift for the ceramic network. Like we went from like broadcast to sync-based, and like data isn't shared with everyone. It's only shared with interested nodes, and that gives us that asymmetry that we're talking about. And a couple of like more interesting observations about this is like, even in the face of new rights, the conversation is always going to end, which is something that we want to happen. And like the reason this happens is, if you go back to looking at this diagram, as we're negotiating these ranges in this key space, like if we haven't yet negotiated a key space and a write comes into that key space, when we get there, you'll discover it. But if we have already agreed that we're in sync and a write comes into that key space, we just ignore it. And then, the next time we sync, we just immediately discover, like, hey, we're not in sync anymore. And since we can keep that tree of all the hashes, it's really cheap to agree that we are in sync, so we can do that a lot. Just go around asking everyone on the network. We use libp2p, we use the DHT to discover peers, and so it's pretty cheap to go through and agree that we're already in sync, and if we're not, it also allows us to we could choose to keep track of those messages coming into that key space and just do gratuitous push, or use gossip sub or whatever else to just return that data back. But currently, we just renegotiate. So the work is going to be proportional to the logarithm of the differences, like I said. So it's really good at finding these contiguous differences. Like whenever there's a 0 on one side, it's just send n pieces, send n pieces of information. And the more interleaved it is, the more expensive it is. So it's potentially an attack vector. It's just generating a ton of interleaved data to try to slow this down. There are some things we know that we haven't dealt with that we will, but generally this protocol is as good as the better splitter. So if one person does something naive, the other does something about in half, they'll split and respond and discover those keys about in the log2 of the person splitting correctly. And here's just an example of something we made to test it. We have a little DSL where we basically define strings of we have 2 nodes, cat and dog, and then we are here's our sets, and we can actually just write out here's what the protocol should do, and then we can assert that indeed that is what happened. Since all the data in the network is binary or encoded, but we can also implement just with strings to make it easier to reason about. So this is a way we test and kind of look at what we're doing, and I think that's about it.